Morning, sir. In this video, I will be presenting the methodology, result, and discussion of my PHY549 project, which involved the simulation of the spring mass system using Scilab. The purpose of this simulation is to study the behavior of simple harmonic motion and to investigate the energy transformation that occur within the system. This is the methodology of the spring mass system simulation that was created using the Scilab. The parameters of the spring mass system were defined in Scilab with the mass of 3 kg, a spring constant of 15 Newton per meter, and an inertial displacement which is amplitude of 0.15 meter. The angular frequency of system was calculated using the equation omega equals to square root k over m. A time vector is from 0 to 10 seconds with an interval of 0.01 second was created to simulate the motion. The displacement and velocity of the mass were calculated using the equation of simple harmonic motion. The potential energy, kinetic energy, and total mechanical energy was computed using the corresponding energy equation. In this simulation, 4 graphs were generated to illustrate. First one is displacement versus time, second is kinetic energy versus time, the third one was potential energy versus time, and the last one is total mechanical energy versus time. Finally, the angular frequency and the maximum value of potential energy, kinetic energy, and total mechanical energy will be displayed in the Scilab console using the displacement function. For result and discussion, the Scilab simulation results show that the spring mass system follow the behavior of simple harmonic motion. The graph show that the sinusoidal shape confirm that the spring mass system undergoes simple harmonic motion. Since no damping force is included in the model, the amplitude remains constant throughout the motion. The energy of the system is continuously exchanged between kinetic energy and potential energy, while the total mechanical energy remains constant. The constant amplitude indicates that there is no energy loss due to friction of air resistance. In this graph, it demonstrates that the kinetic energy continuously changes during oscillation and reaches its maximum value when the mass moves fastest through the equilibrium position. Kinetic energy reaches its maximum value when the mass passes through the equilibrium position x equal to 0, where the velocity is highest, and kinetic energy becomes 0 at the maximum displacement point x equal to 0.15 meter, where the velocity is 0. The graph always remains above the x-axis because kinetic energy cannot be negative. In the third graph, it shows that elastic potential energy is continuously converted into kinetic energy and back again during the oscillation. Potential energy is maximum when the spring is fully stretched or compressed, and it becomes minimum at the equilibrium position x equals to 0. The kinetic energy and potential energy graph show a continuous exchange of energy throughout the oscillation. The kinetic energy is 0 because the mass stops momentarily before reversing direction. At the equilibrium position, the mass has maximum kinetic energy because the maximum velocity is there and the minimum potential energy is present in the mass. And the last graph is the total mechanical energy graph, show that the energy of the spring mass system remains approximately constant throughout the oscillation. As the mass moves, energy is continuously exchanged between kinetic energy and potential energy. When the kinetic energy increases, the potential energy decreases by equal amount, and vice versa. As a result, the sum of kinetic and potential energy remain constant at approximately 0.5625 joule. Although the graph appears to show slight fluctuation, these variations are caused by numerical rounding error in Scilab and do not affect the overall result. The constant of total energy confirm the law of conservation of mechanical energy indicate that no energy is lost from the system since damping, friction, and air resistance are neglected in the simulation. And the last one, for numerical result, the angular frequency represents the rate at which the mass oscillates about the equilibrium position. It is calculated using the equation omega equals to square root k over m. The obtained value of 4.0825 radian per second indicate that the spring mass system oscillates relatively rapidly. A larger spring constant or a smaller mass will result in the even higher angular frequency. In maximum potential energy is occur when the spring reaches its maximum displacement, 0 is equal to 15 meter. At this position, the velocity of mass is 0 and all the mechanical energy is stored in the spring as elastic potential energy. The results show that the spring stores a maximum of 0.5625 joule of energy during its oscillation. Next, in maximum kinetic energy, the maximum kinetic energy occurs when the mass passes through the equilibrium position where its velocity is greatest. The value obtained is extremely close to the potential energy. The slight difference is caused by numerical rounding during Scilab calculation. This result confirms that the energy stored in the spring is completely converted into kinetic energy during the motion. And the last one is total mechanical energy. That the simulation show the total energy remain constant at approximately 0.5625 joule throughout the oscillation. This confirms the law of conservation of mechanical energy, which states that energy cannot be created or destroyed, but can only be transformed from one form to another. Since the model does not include friction of damping force, no energy is lost from the system. So overall, the numerical result obtained from Scilab agree with the theoretical principle of simple harmonic motion. The angular frequency of 4.0825 radian per second describes the oscillatory behavior of the system, while the maximum kinetic energy and maximum potential energy are both approximately 0.5625 joule. The constant total mechanical energy demonstrates that energy is conserved throughout the motion, validating the accuracy of the simulation and the theoretical model of an ideal spring mass system.